All right, for this part, we would like to give you a general idea about how we do the data cleaning, data selection, and also data transformation. So the first thing first, we would like to show how many features we have in this data set, which is 47. And we also want to know how many missing values we have. And then it turns out 22 of the features have the missing values. And here shows how these features miss the values. Another thing we did is to check the duplicates, and the good thing is there's no duplicates in our datasets. Now we're going to move to the data transformation part. The first thing first, we also want to make sure the DTI, which is debit to income ratio, is not a negative number. And also we do the data transformation on the months here. From the January to December, we transform it to the 1 to 12 in order to do some correlation tests for the next step. And another thing which is also really important in our data transformation part is to change the grading scale. The grading scale in this data set is from the A to G, and we want to change it to the 1 to 6. By doing that, we can make sure it's a numerical based feature. And here is a little bit correlation we did here. It is obviously a little bit messy, but by looking at here, we can see how these things are correlated to each other. And we also noticed that there's one feature named employment length have a lot of missing values, and we also believe it is really important in our data sets. So what we did is we use a random forest to using the existing values to predict the missing values. Due to the time we have, I will probably not show you how we polish model section by section, but I will just directly show the final results we got. And it turns out we have a 0.8 accuracy, which means the model have a good ability to classify the non-default and default values. And also the ROC AUC score is 0.73, which is also pretty good. And we also do some cross-validation, including the 5-4 cross-validation, and the model still have a pretty good accuracy rate. The ROC AUC score is still very good. Another thing we did is stress testing, which means we want to show whether the models still have a good performance in the stress environments. So basically what we do is we change the GDP rate and also the unemployment rate. We plus 5% on the unemployment rate and also decrease the GDP rate a little bit. And still, it turns out we have a good rates. The accuracy rate is still remains 0.8, and our CAUC score is still 0.73, which means the model has passed the stress testing, and they still have a good performance under a stressful environment.
Two main models were employed for the logistic regression model: gradient boosting machines, or GBM, and stochastic gradient descent classifier, SGDC. GBM was initialized without explicitly stated in estimators, implying the use of the default number in boosting. This model is known for its capability to reduce both bias and variance in the dataset. SGDC was initialized with a logistic regression loss function, specifying that it's geared towards classification tasks, with max epoch set to 1,000. The dataset was split into training and test sets with the 80-20 split with a random state of 42 to ensure reproducible splits. K-fold cross-validation was applied during the training to minimize variance. We used the initial set on the GBM SGC models to generate predictions for the test data, which were then used as input features for the logistic regression model. The logistic regression model was then trained on the predictions from the GBM and SGD classifier and subsequently tested on predictions from these models. Performance of the logistic regression was measured using accuracy, ROC, and AUC score. The ensemble model demonstrated substantial predictive accuracy with an accuracy rate of 80.46%. This high level of accuracy indicates that the model correctly identifies the majority of outcomes, making it a reliable tool for assessing credit risk default. The model's ROC AUC score is approximately 0.725, implying the model has a good discriminability between defaults and non-defaults, as demonstrated in the graph.
In order to incorporate our random forest classifier into our project, we imported our data and we read in our libraries. We identified the columns that will be used in our classifier, excluding any non-relevant, non-numeric columns. And we normalized that data because we wanted to use k-nearest neighbors, since k-nearest neighbors requires normalization. We identified an n of clusters or number of clusters of 3 as the most relevant to our specific project. In later iterations, we did utilize a loop to identify the number of clusters based on silhouette score that would improve our model performance. However, in clusters of 3 was the most robust in that regard. We also included distance to central centroids or cluster centroids as additional features in that model. And so we move right into our classifier and how we implemented it. We split our data into our test and our split, initialized the classifier on the baseline model, and calculated the accuracy in ROC AUC. What we did see was that the accuracy was very high, although the ROC AUC was no better than guessing. Initializing the random forest again on the model with our cluster labels, what we did see was a marked improvement in both accuracy, rising from 0.807 to 0.85, and in ROC AUC to 0.64. Both of these are not super exciting, but we did see an improvement, which confirmed one of the objectives of our study. And so, in conclusion, although the accuracy was high, it can be misleading where data sets are imbalanced. And this also gave validity to our further amendments to our project where we balanced our data set and looked at its performance. Thus, further iterations were done, including cross-validation and hyperparameter tuning, as well as, like I mentioned earlier, utilizing the loop to identify the number of clusters of best performance based on silhouette score. However, that actually worsened our performance compared to our baseline model. So this specific run was saved as our most ideal, and the random forest was scrapped ultimately as a non-performer compared to our other models of choice.